All right, now we've done a discussion about momentum. Now we're going to talk about collisions, when two objects come into contact here. So there are two situations where we will often deal mathematically with collisions, and we call the first type an elastic collision, and the second type a perfectly inelastic collision. But the truth is there's a third type that's just plain old inelastic. Not perfectly inelastic, but plain old inelastic. So if you look in any collision, the first thing that is always conserved, regardless of which of these three types we have, momentum is always conserved. So for any type of collision, your initial momentum will equal your final momentum of all bodies that were in motion before and after the collision. Same thing is true for perfectly inelastic or plain old inelastic. Momentum is always conserved before and after collision.
Is it because Newton's third law?
So you could look at it in that context. But in this case, you just definitely need to know that momentum is always conserved. It doesn't matter the kind of collision. What's not necessarily conserved is kinetic energy. For an elastic collision, kinetic energy is also conserved. But for inelastic collisions, whether it be just plain old inelastic or perfectly inelastic, kinetic energy is not conserved. So your initial and final are never the same. Your final is always not necessarily zero, but less, smaller. You always end up with less kinetic energy. So in inelastic collisions, you always lose kinetic energy. So in a perfectly inelastic collision, the amount of kinetic energy you've lost is at a maximum. In a plain old inelastic, you haven't necessarily lost the maximum, but you've lost a fair amount. Now, the hallmark of a perfectly inelastic collision is that the two objects that have collided, or if there's more than two, but in the case of two objects colliding, they are stuck together. If they stick together, you have a perfectly inelastic collision. If two objects collide and have no propensity to stick to each other, no propensity for any kind of permanent deformation or anything like that, that's probably where you're going to get as close to an elastic collision as you can come. And the classic example is billiard balls colliding on a pool table. Yeah, billiards. Sweet. So these billiard balls on a pool table, do they have any propensity to stick to each other? Not really. Do they deform upon collision much? Not much at all. Hardly noticeable amount. And so that would be as close, it's kind of our textbook example of an elastic collision. So the truth is, though, there's no such thing as something that's completely, perfectly, absolutely elastic. Just our best approximations. And in this case, for our theoretical elastic collisions, yes, kinetic energy will be conserved. For every other kind of collision, whether it be plain old inelastic or perfectly inelastic, you're always going to lose some kinetic energy. But again, one more time, for any collision period, what's conserved? Momentum. Great. And you can deal with this in more than one dimension. In a single dimension, if the objects before and after are only moving on a straight line, within a straight line path, one direction or the other, that's a one-dimensional problem, and momentum will be conserved in that one dimension. But if all of a sudden you have components of velocities in both the x and y directions, then all of a sudden you'd have a two-dimensional problem, and you'd have momentum in the x direction is conserved, and momentum in the y direction is conserved. Potentially, though, we could make this worse and make it a three-dimensional problem. And instead of things just moving in the x and y, now we also have them moving in the z, and then you'd have three conservation of momentum equations, one for the x, one for the y, one for the z. You're not so likely to see that, but two-dimensional, totally common in this section. So we'll deal with one of those here in a little bit. So let's see how to apply this lovely stuff. Let's look at question number 3.